Hello and welcome back. Today we're going to continue with Huffman coding we transition from brute force algorithms and divide and conquer algorithms over into some coverage of data structures. Remember, the course is called Data Structures and Algorithms, so we do need to cover some data structures as well. All right, so we left last time talking generally about coding theory, where there are these two basic branches where one is to add information so that you don't lose information over a noisy channel. The one that we're interested in, though, is compression, where you remove redundant information so that you're making data smaller so that it can be stored with less disk space and stuff like that. There are plenty of lossy compression algorithms that you're well familiar with, like JPEGs and MP4s and MP3s, that get rid of redundant information or use mathematics to approximate an image so that it can, make it as small as possible. We're looking at Huffman coding today, which is a lossless compression algorithm. So it's going to try to take advantage of the fact that English has a lot of redundancy. For example, the letter R is far more common than the letter Z. And in fact, if we've got a text file, say, where there is no Z at all, then we don't need to encode it at all, right? We don't even need to consider that in our encoding scheme. What we're ultimately going to do is we're going to create an encoding where the code words are smaller for more common elements and they're longer for less common elements, rarer elements, rarer symbols, basically. Okay. Before we do that, we need a little bit of background, though. So what is an encoding? An encoding is a mapping of symbols, and in our case, that means that characters. It doesn't necessarily have to be a character set like an ASCII character set. It could be a set of words, right? So you want to encode an entire word or a sequence of characters or something. Or it could be something that's not even English. It could be a DNA sequence, right? Where you're encoding for the four basic amino acids. It's a mapping of symbols to binary strings, right? And you're already familiar with this with respect to the ASCII text system. A block encoding is a mapping that maps all symbols to code words, right? That is bit strings of the same length, right? So ASCII would be an example of this. Now, technically, ASCII is only 7 bits. Let's consider the extended ASCII character set where they have 8 bits. A is represented by 60. Capital A is represented by the number 65. The binary representation of 65. Let's see, 001 00001. Then that's the don't quote me on that, but that's the bit string representing that character in that character set. So, for example, ASCII, right? In general, block length encodings require order, or in general log base 2 of n, require code words of length log base 2 of n. And you can see this with ASCII. Again, if we consider the extended ASCII character set, where there are 256 unique characters, including non-printable control sequences, log base 2 of 256 is, guess what? 8, right? That's going to require that many bits in each code word in order to encode it. But you don't have to encode it like that. Alternatively, you can use a variable length encoding scheme, right? Where each code word may be of a different length. Right? So, for example, let me go ahead and go over here to the iPad. Let's go ahead and come up with just a simple 4 code word code, including the code word 0 01, 101, and 010, right? That's going to be a variable length encoding scheme because there are some code words that are only 1 bit. There's another code word that is 2 bits, and then there are 2 code words that are 3 bits, right? Now, there immediately arises a problem when you start using variable length encoding schemes. Suppose that I encoded these as A, B, C, and D, right? And suppose I encoded something very short message like 010, right? And I sent that through my channel. Sometimes this is referred to Alice speaking to Bob. Right? And Bob receives, say, the same exact code word over here. But Alice over here had encoded, say, A, actually, let's go with, sorry, B, A. Right? But on Bob's end, it's kind of ambiguous. He could decode this as BA, or he could decode this as just D. How does he know the difference? Well, to solve this, that means that through between every code word, you're going to have to send some sort of additional signal, not just another a delimiter basically, where I'm going to have to say, here's my code word delimiter, here's my code word delimiter, here's my code word delimiter. Unfortunately, that blows up the amount of information that you have to send over the channel. So what we want is what's called a prefix-free code, right? You'll note that I've gotten it. I can undo it. You'll note here that A is a prefix of D. In other words, this code word appears as a prefix to the rest of this code word. Likewise, B appears as a prefix over here to D with the first 2 bits. So we could actually have decoded this as what else? BA or AB? Maybe those are the only 2. But in any case, it's ambiguous, right? So let's go ahead and go with what's called a prefix-free code. So I'm going to go ahead and write a different code here. It's going to be still variable length encoding. 100101110 and say 0110, right? And now you can verify visually by visually inspecting this here that no code word appears as the prefix of another code word. 10 is not a prefix of this one, it's not a prefix of this one, it's not a prefix of this one. Likewise, 010 does not appear as a prefix of either one of these. It disagrees in at least 1 bit in each one of these. And now it's completely unambiguous. When I get when we send a signal, all it has to do is start. Well, initially, if it reads a 1, okay, it could be this one, or it could be that code word. But then the next bit that it receives, say, is 0. That means, oh, it must be this, and I can decode that right away. If it received a 1, it could say, okay, well, it could be this. It probably is. So if it's the next one is a 0, yep, that's the code word. Decode it, right? From A, B, C, D, or whatever you're trying to encode. So a variable length encoding scheme either needs delimiters, which we're not going to, that's not the solution we're going to go with, or it needs, besides, if you have a delimiter, you can actually just rewrite the code so that it's just binary, but it's prefix free. Or we go with a variable length encoding scheme here that is prefix free, right? And that's the route that we're going to take here, okay? So the problem is that a variable length encoding may be ambiguous. Right? We need to use a prefix-free encoding scheme. Moreover, what is our goal here? Our goal is compression. So what we're going to do is we're going to associate common or high frequency. In other words, they frequently appear in the file that we're trying to compress. Code words with shorter frequency, symbols with shorter code words, and less common or rarer, low frequency words with, or symbols, sorry, with longer code words. And the goal here is ultimately that we want to re-encode this thing, not in ASCII. Of course, you could always, in fact, that's the input to your assignment. We give you an ASCII text file, which is implicitly encoded in ASCII, and you're going to come up with a different encoding that is going to be a smaller size. With ASCII, of course, everything is 1 byte. So if I give you a 1,000 character file, that's going to be 1,000 bytes, right? And you're going to want to get that down so that the ultimate encoding is going to be less than 1,000 bytes, okay? All right, so here's the idea. In fact, instead of talking about the idea, what I want to do is I want to illustrate it visually. Right? So let's go ahead and transition over here. Here is a potential input to Huffman Coding. Now, the way that you should read this is that the file that we're trying to encode has 1, 2, 3, 4, 5, 6, 7 characters. This is just a toy example. Of course, in a real text file, you would have probably all 26 characters, including spaces and endline characters and things like that. But just to keep it simple, suppose that we have this encoding right here of A through G, all capitals, whatever, right? We have already pre-computed the frequency. That's something you're going to have to do when you program this. You're going to have to go through the file once, compute the frequency, and then build an encoding scheme. But suppose that we've gone through the file, and the way that you read this is that 10% of the characters in the file are A's, 15% are B's, right? D is the least is one of the least frequent characters, and it appears only 5% of the time. Here, G is the least frequent character. It appears only 3% of the time. C is our most frequent character, appearing 34% of the time. Right? So again, my goal is to build an encoding scheme such that these least common characters have longer code words, and these more common characters, C as well as F, they have shorter code words. The tool that I'm going to use to do this is a tree, and you'll see why after we've built it. I'm going to start out with a bunch of tree nodes, not a bunch, but one tree node for each character that I want to encode. And I'm going to draw them as boxes here. Right? So here's A, 0.1, and here's B, 0.15, here's C, 0.34, D, you can delimit them if you want to, E, F, and G. But I won't rewrite the frequencies because we've got them up here. Okay. So these tree nodes are not connected. They're just 7 nodes that are sitting over here on the side. And what I'm going to do is I'm going to want to combine them in a way such that I build a binary tree. Now here's the intuition. The binary tree, the path, remember there's exactly one path from the root to any leaf node or any node period in the graph or in the tree. So what I want to do is I want to make sure that that path is going to represent the code word. You'll see here in a moment that if we go one way, we're going to associate that with a 0. If we go a different way, we're going to associate that with a 1. But now the tree, what I want is the deeper that these characters are in the tree, the longer the code word. The shallower that they are in the tree, the shorter the code word. So my strategy is going to be a greedy strategy, where I take the 2 least common code words, in this case D and G, and I combine them first, understanding that they're probably going to be down in the bottom of the tree. Okay? So I'm going to go ahead and take, what was it, D, right, and G, and I'm going to combine them into a new tree node. It doesn't matter if you go left or right. I could have put D on the other side. I could have put G on the other side. It's arbitrary. In this case, I put the larger node in the left and the smaller node in the right. Just be consistent about it. In fact, you don't even need to be consistent about it as long as it happens, right? Now, I'm going to associate a new parent node with those two nodes that is going to be the sum of its frequencies. Because the idea here is that everything in this smaller subtree is going to have a combined frequency. What is the probability, or what is the frequency of D or G? If I were to randomly pull out a character from the text file, what is the probability that it's going to be D or G? That's going to be 5% plus 3% for a combined total of 8%, or 0.08. Okay? Now, don't think of this as I've got 1, 2, 3, 4, 5 tree nodes over here and one tree over here. I've got 1, 2, 3, 4, 5, 6 trees. One of them just happens to be 3 nodes, and the rest of them just happen to be 1 node. Right? Continue. What I mean by that is that tree gets thrown back into the mix, and I've actually got 1, 2, 3, 4, 5, 6 trees that I'm dealing with now. Right? But I will keep it over here. Okay. Now, I've taken care of D and G. I need to continue. I'm going to combine the two least weighted nodes, trees, period. Right? And this one now has 0.08, so it's now the least. I'm not looking at D and G individually. I'm looking at the tree itself, and it's weighted 0.08. That's the least. What's the next least? Looks like it's A to me. So I'm going to combine both of those into one tree node. And it has a total of 0.18. Right? And I've taken care of that. Now again, I have now 5 trees. Now I'm down to 5 trees. This tree happens to have a weight of 0.18. This tree still has a weight of 0.15, excuse me. This has a weight of 0.34. E has a weight of 0.12, and F has a weight of 0.21. Right? So I continue. I combine the two least weighted trees. At this point, that's going to be B and E, because this tree over here has 0.18. So B and E. And again, it doesn't matter which side you put each one on. I'm just going to combine these two into one tree. And B has a weight of 0.15. E has a weight of 0.12. So they combined have a weight of 0.27. Okay? 0.21, 0.34. Now I've got 4 trees. The two least weighted trees are now going to be F and this tree over here. I'll go ahead and combine those. And that's 39.39, excuse me. There we go. Now I'm down to only 3 trees. The two with the least weight are going to be 0.34 and 0.27. So let's take this and go ahead and combine it into a tree that is 0.61. And at this point, I've only got 2 trees. And so I'm going to combine those as one node that sums to 1. Right? The frequencies should sum to 1 or thereabouts in practice because they're frequencies. This one appears 10% of the time. This one appears 5% of the time. They have to sum up to 100% or 1 in this case. Right? Now, let me go ahead and get rid of this. Oops. No, let me get rid of this. Right. And erase some things. Erase my scratches. Now here is how we develop the actual code. Okay? 0, 1, 0, 1. Here you do have to be consistent about it. I will associate 0 with any left child and 1 with any right child. You can, of course, flip those around if you really want to and associate 1 with a left child, 0 with a right child, and you would come up with an equivalent code. Now, how do I get the code word representing, say, B? I start at the root, and I travel down the tree until I get to that that letter. Right? You'll note here that all of the letter nodes are represented as leaf nodes. Right? That's because of how we built the tree. Not only that, but the least weighted nodes down here, D and G, they're deepest in the tree, whereas the more common nodes are going to be shallower in the tree. That's going to give us the property that we want. B is going to be associated with a code word 000, because that is the those are the bits associated with that path going down to B. What about E? 001. So E is going to be 001. What about A? Where is A? Down here. It's going to be associated with 100. Just making sure that that appears. Yep, looks like it's on screen. Good. What about C? Where is C? It's over here, and it's going to be associated with 01. Right? There is no leading 0 here, otherwise that would get us right back to square one with a block length encoding. What about D? D is way down here at the bottom. It's associated with 1010. Being one of the least common characters in here, it also consequently has a longer code word, a code word length of 4. E, F, G. All right. G is going to be associated with 1011. F is going to be associated with 11. Right. And I got them all. So the code word lengths here are 3, 3, 2, 4, 3, 2, and 4. So one way that you can measure how good the compression was is by coming up with something called a compression ratio. That is, if I were to actually encode this file, and everywhere that I see an A, I go ahead and replace that with 100. Every time I see a D, I replace that with 1010. And of course, taking my code and putting that into the file as metadata, that here's the decoding sequence that you need to decode the rest of it, right? You're not going to go that far. You're just going to report it to the standard output. But the measure that I could come up with is taking the code word length times the frequency and sum it all up. And that gives me the average code word length, right? On average, that if you pulled out a random character from the file, you could expect that it would be encoded with, say, 2.5 bits or something like that. Again, it's an average. So all I need to do is come up with the frequencies. And for that, I'm going to have to restore my image here. Oops, sorry. There you go. I'll put this down at the bottom here over everything. So the character frequency on A was 0.10. The character frequency on B was 0.15. Right? 0.34. 0.05, 0.12, 0.21, and 0.03. And if I multiply all of these together and then add them all up as a sum, I'm not going to do that. That's just algebra at that point. Let me go ahead and find out what it was. It's going to end up being 2.53. Right? So what is the interpretation of that number? With the Huffman coding, the average code word takes 2.53 bits. Right? Now, of course, you can't actually, none of the code words actually have a fractional bit because that doesn't make any sense. A bit is a bit. It's either a 0 or 1. Some of them are 3. Some of them are 2, some of them are 4, but the average is 2.53. With ASCII, right? Well, the average is fixed, right? It takes 8 bits, right? But if we were to be smart about this and not use ASCII and use a block length encoding, then it would take log of base 2 of however many symbols were in our alphabet, right? And in this case, we had A through G, which is 7 symbols. So log base 2 of 7 is, well, you need here you can't take a fraction because you can't it's going to be slightly less than 3. But you're going to be forced to use 3 bits for every single code word, and then 1 bit string of length 3 is just going to be unused. So generally what we do is we take the ceiling of this, and this is going to end up being 3. Right? So we compressed the file. It went from an average of 3 bits per character down to 2.53 bits per character. And again, this is a toy example, but you can also come up with a compression ratio. 3 minus 2.53, that's your savings, how many bits you saved. This is the original, that's how many bits were required for a block length encoding. And when you come up with this, then it's about a 15.67% compression. Right? So if it had like a 1 megabyte, it's been compressed down to 15%, so that's something like 850K instead, right? And all of that, all of those stats, you should be reporting that with your program. You can report additional stats if you really want. Compare it to both ASCII and a block length encoding scheme. Now, sometimes people reverse this and say, well, I compressed it by 15%. The resulting compressed file is 85% of its original size, and they use that as a compression ratio. It's the same thing. Do you get a 15% discount, or is the price 85% of what it was? Right? It's both. Yes, it's still true, whichever perspective you take. Okay. Okay. So that's Huffman coding. Let's go ahead and, that's my explanation of it visually. How do we actually say code something like this up? So you might have to pre-process the file, and then when you actually go to program this, you'll have to go through the file, count up the number of A's, count up the number of B's, count up the number of C's, etc. And that should be pretty straightforward. So we'll just assume that that's a given. So our input is an alphabet of symbols. And usually we use sigma as our alphabet with frequencies. Say, I'll just go ahead and go FREQ for short here. So X is a symbol, and FREQ is the frequency of that symbol. For our input over here, it would end up being A is our symbol, and then 0.1 is the value that's given. Right? And that's a part of our input. Our output will be a Huffman tree. Once you have the tree, then you still need to produce the code by walking around on the tree, right? Like we did over here. And you can use any tree traversal algorithm that you're familiar with, pre-order, post-order, in-order, whatever. Or you can keep track of each one of the leaves independently and then just take a walk up to the root. 0, 0, 0, and then reverse it. No different there. C would be 1, 0. And then you'd reverse it. In fact, I don't think you even need to reverse it. I believe, yeah, you could just go ahead and go 1, 0, and that would produce an equivalent code. Just like switching these around and using 0 over here on the right child and 1 over here on the left child produces an equivalent code. It's an equivalent code in that all of these code word lengths would stay the same. The code words might change around, but you would still have a a prefix-free variable length encoding scheme. Before we talk any more about the algorithm, why is it prefix-free? Did we achieve our goals? We achieved one goal in that more common code words are shallower in the tree, and more rare or less frequent code words are lower in the tree, by virtue of the strategy that we took for building it. But what about a prefix-free code? Certainly, you can look at this visually and say, yes, that is a prefix-free code. No code word appears as the free prefix of another code word. Why? That's the nature of the tree, right? Let me go ahead and suppose that we had two code words that were 0, 1, 1 and 0, 1, 1, 0, right? Suppose that our tree produced this code word. What would that look like? We would have gone left, then right again, right? And that would have been a letter, say A. And then we would have gone left again, and that would have been B. That can't happen because of our observation here that all of the letters are associated with a leaf. And there's no inner node that contains a symbol here from our input. So therefore, because of the uniqueness of a path from the root to any node, and the fact that all of the symbol nodes are down here as leaves, means that we get a prefix-free code out of this algorithm. Okay. All right. So again, you might have to, especially when you program this, you are going to have to pre-process the file to find all the frequencies. You're going to have to post-process the Huffman tree in order to actually produce the code. But here's what the actual Huffman algorithm looks like. Right? So I'm going to initialize this thing, H, to keep track. It's going to keep track of nodes. Right? So now you might be, we got a question here. I understand how you got the binary represent numbers 1, 0, 1, 0, but how did you get 3, 2, and those numbers? I'm lost there. So I assume that you mean these over here, right? Those are just the length of this code word. How many bits does it take to represent A? That's 3. How many bits did it take to represent B? 3, 2, 4, 3, 2, and 4. Right? These numbers, the frequencies, that was given as part of the input here. Hopefully that answers the question. Sorry I didn't see that sooner. All right, so what are we going to use to keep track of these nodes? Remember our strategy over here. We wanted to take the least frequent first. I want the least frequent and then the second least frequent. I will combine them, creating a new tree node, and then throw it back into the mix over here. And then I want the next lowest, and then the next lowest, and the next lowest, etc. Right? How do I go about doing that? Hopefully you remember that there's this nice little thing called a min heap. Right? A min heap is a collection data structure that holds things, and you have two operations. You can push and you can pop. Pushing means you're throwing something onto the heap. Where it ends up in that heap, who knows? Popping means that you're getting the minimum element out of that heap. So I'm going to throw everything onto the heap, and I'm going to get the minimum out of it with respect to the frequencies, get the next minimum out of it, and I've got my two nodes that I can combine, and then I'll throw it back onto the heap. Where it ends up, that's the heaps problem, right? All right, so for my initialization here, for each x, symbol x, in your alphabet, sigma, I'm going to initialize a new tree node. So t sub x is going to be a new tree node. And I'm going to associate it with a weight. The weight of t sub x is going to end up being the frequency of x. Right? Just like I drew it over here, right? I drew C and then 0.34 here. I'm putting both of those pieces of data into that node. Okay. And I will insert h dot push t sub x. Right. I'll use proper. Now, ultimately, this is going to be what's called a priority queue, and that's why we're calling them push and pop. I prefer calling them NQ and DQ, but your mileage will vary, whatever you want to call them. I'm putting something on the heap, and that's all. Right? That's my initialization. While I still have stuff in the heap. When did we stop? We stopped when we pulled everything out and we only had one single tree. So if I'm going to put all of these nodes into the heap, and I'm going to pull them out, well, I only need to stop when I don't have anything else to pull out, and there's my tree. So while the size of h, in fact, let me go ahead and shorten that up, h dot size is strictly greater than 1, right? I'm going to need to give myself some more room here, so unfortunately I might have to go to the next slide. But otherwise, what I'm going to do is I'm going to create a new, create a new tree node. That's going to be the parent of the two that I pull out. So I'm going to use different variables here. I'm going to call this P because it's going to end up being the parent of the left and the right. And so TL and TR, I'm just going to pull out the minimum value pop from the heap and pop from the heap. Right. Dot, dot, dot. I'm just going to go on the same slide here. And so I'm still on the same block here. And I'm going to make T sub parent dot left child. I'm going to associate that with T sub L, and T sub P dot right child will be the second one that I pulled out, T sub R. Okay. And then I need to update the weight of T sub P. And I'm going to be setting that equal to, here, I'll use the arrow syntax here. That's going to be the weight of T sub L plus the weight of T sub R. Right? Remember when we drew it, all I did was take the weight of the left child, take the weight of the right child, and then that became my new weight. I added them together. Okay. And then what I'm going to do is I'm going to throw it back into the mix. So H dot offer or push T sub P, that new tree. There. I'm taking two things out, combining them, and throwing them back in. The fact that I can take out the two smallest or least weighted trees automatically for free from the heap is the magic of the data structure, smart data structure. The fact that I can throw it back in efficiently is also something to worry about with respect to the heap. I don't have to worry about that, right? I'm just using that data structure to accomplish a goal. When I'm done, I output h.pop. Right? Note here that I went with strictly greater than 1. So when I break out of this, there's one tree left in the heap, and I simply pop it out, and that's my Huffman tree. The tree with a weight of 1, right? And this entire structure. Then I can hand that off to another algorithm to actually walk around the tree and produce the code word for each one of those symbols. Okay. So what about an analysis on this? Right? We'd have a couple of operations here: a push operation and a pop operation, and we do it here, here, etc., and we do a push here. Hopefully you remember that. Let me go ahead and get rid of this. Hopefully you remember how heaps work. If not, we will give a short review right after this. All right. But remember that for an efficiently, at least for an efficiently implemented heaps, the push and the pop operations are both going to be order log n. And it's not necessarily the way that we present heaps is usually as a tree, but it doesn't necessarily have to be implemented that way. Or you can use a built-in data structure, which we'll do here in a second. I'll demonstrate that really quickly. But otherwise, it's you're pushing things in, you're taking them out. Okay. And I'm doing this how many times? Let's just look at the initialization phase here. I'm building a tree and pushing it in, building a tree and pushing it in, right? So note here that the size of the heap is actually growing, right? So let's think about the initialization phase, right? What I'm going to do is I'm going to execute this for a number of iterations. Remember that there are n symbols, so I will have n iterations. The size of the heap is changing. On the first iteration, there's nothing in the heap. On the second iteration, I've already added one symbol to it. So it's going to be of size 1, and then I'm adding another one, and that gives me a size of 2 on the next iteration. And you can see the pattern here all the way up to n minus 1. Right? So the insert or the push operation complexity is going to be dependent on the size of the heap on each one of these iterations. This doesn't make much sense, but I'll write it down. Log of 0 is undefined. It does not give you an infinite infinite amount of money. This would be like negative infinity, right? Something like that. That doesn't make any sense. So I'm going to immediately cross that out and say it doesn't cost me any comparisons. It will cost you one comparison to insert into a heap of size 1. You have to know whether or not the thing that you're putting in belongs as a child or as the parent of the current element. So that's one comparison. Log base 2 is going to be, well, you can write it out, but let me go ahead and get rid of this and keep it in symbolic form here. Of course, I've already said get rid of this one. ... until log of n minus 1. So in other words, the grand total here of this complexity is going to be log of 1 plus log of 2 plus log of 3 plus ... log of n minus 1. That's the number of comparisons that or heap operations, basically, that we're going to end up doing. The number of comparisons from the heap operations that we're going to end up doing with that initialization phase. Again, we're only focusing on this first part right here. Right? Okay. Well, hopefully you remember your log identities. Log of A plus log of B. I can combine that into log of AB. I can apply that log identity to the first two. Once I've collapsed them into one, I can apply it to the second two, and I can apply it all over the place until I get that this is equivalent to log of 1 times 2 times 3 times 4 times ... n minus 1. Okay? Or another shorthand way of writing that is log of n minus 1 factorial. All right? Now that might look big. N minus 1 factorial is big. But you're taking the log of it. Right? This is going to be less than or equal to log of n to the n. Hopefully that's easy to see because each one of these terms is less than n. I'm giving a loose bound here. 1 is less than n, 2 is less than n, 3 is less than n, n minus 1 is less than n. So if I replace each one of these terms with n, then I have n times n times n times n, n raised to the n. And that is simply equal to log n, another log identity here. You can take n out to the front, and you're left with n log n. In other words, it's order n log n. Just as good as sorting, just as good as heap sort when you're using a heap to sort stuff. You're putting stuff in, you're taking stuff out. That's exactly what we're doing here. And that's why I only focused on the initialization here. We put in n items. We take out n items. Right? Now, granted, we take out the 2 items and then we throw something back in. So this second phase right here is going to be twice as complex. It's going to end up being 2 n log n. But with big O analysis, again, we ignore constant terms, constant coefficients, and it basically ends up being order n log n for the entire thing. Okay? Now, producing those is going to probably be, producing the actual code words is probably only going to be linear. Computing the frequency is going to depend on the size of the file, not the number of symbols. But those are not what we're focusing on here with respect to the Huffman algorithm itself. How do you use this heap, right? How do you build a heap? I'm going to save that for a second here to remind. First of all, you should go back to Computer Science 1. I've got a full set of videos on that from 156 where I walk you through how to implement a heap both as an array versus also you can also do a tree representation. It's a little bit trickier because you do have to find where you insert stuff into the tree, and that is non-trivial. But what I wanted to do is, since most of you are using Python, is talk about the built-in, right? You don't roll your own heap. There is a built-in, at least it's in a library, I believe. Let's see, where is it? Let's see, I never opened that up. Okay. There we go. There's a library called heapq. Import heapq. Right? Now, what does the Q stand for? They name this as a heap queue. That's because a heap is an efficient implementation of a priority queue. That you've got a priority line, basically, where when you put something into the line, you have a priority, right? The items with the highest priority, or in this case, since it's a min heap, the least value, are going to be able to jump to the head of the line. Right? They're VIPs. They're very important people. They get to line jump. Sometimes people will have or elements will have a priority that is somewhere in the middle. So they get inserted somewhere in the heap, but it doesn't matter because the next person with the highest priority is always served next out of the queue, or the priority queue. That's where the queue comes in, right? How do you use this? Well, if you already have an existing array or list, excuse me, for example, let me just go ahead and cut and paste this. This is not a heap, right? This does not have the structure of a heap. So what you need to do is you need to heapify it. You need to fix it so that it is a heap. And there is a built-in function to do that, heapq.heapify, right? And let me print it out and see. It's still a list. It's just that it now has what's called the heap property, which we might talk about here in a second. So Python 3. This is demo. Right, there we go. So it's been changed. Right, before it was 1843 ... It's not sorted. We can see that immediately with 8 does not come before 5, but it does satisfy the heap property already. Right, and I'll draw that out here for you in a second. You can add stuff. So heapq.push, and this is why I was using those terms: push, enqueue, offer. Insert, whatever you want to call it. Let me go ahead and insert 10. And let me go ahead and insert -10. Got a question online. Thank you. Sorry. I'm an idiot. There we go. Apologies. Let's go over that again since I was not displaying that. The library is heapq, and again, the Q stands for Queuue. That's what it stands for. If you have an existing array here, or an existing list, then you can heapify it using heapify, and it changes it. So this is what I was referring to over here. It's 01138. It's not sorted, but it is. It now conforms to what's called the heap property. That the next thing that I pull out is going to have the highest priority. This is a min heap, so it's going to give you the least valued element in that list. Okay. If I push 10 and push -10, now the way that you have to do this is you have to give it the heap. Unfortunately, this is not really a way of doing it object-oriented, where you've got a heap and then you can call methods on that heap. You've got this method in this library, and you have to give it both the heap and the element together. But it will work. Let me go ahead and print it out again. And we can see, oops, sorry, it's not push, it's heap push. There we go. There we go. So you can see that 10 kind of had a lower priority, so it kind of went to the back of the line. Now it has a lower priority than even 3, but again, it's not sorted. it's conforming to the heap property. Okay. -10 gets to jump to the front of the line because it has the least priority there, right? Again, it's a min heap. This is the front of the line, and then everybody's just standing around in the room like they've pulled a ticket. Now serving number 5, now serving number 6, right? They don't have to stand in the line. They can just wander around the room. These things are just, it's a pile, it's a heap, and they're somewhere in the pile. And then when their name is called, they get to get up out of the pile, right? They're on, etc. Right? So you can push stuff. You can pull stuff out. So x is equal to heap q dot. Now make sure that I get the right one. Heap pop, yes. Heap pop, and again, you need to provide it the heap. In this case, a, and I can print that out, and then I can print the heap again to verify that it has been popped out of the heap. So -10 was the next one that we're going to be that's being served, and it's no longer in the heap. Cool. Now you might be asking yourself, wait a second, how am I going to use this for the actual programming assignment? Because they're not integers. It works with anything that's comparable, and it also works with tuples. So if you want to, you can also push other elements. So I'm going to start out with an empty heap here, right? And I will have heap q dot push onto h a tuple. Right? Now by default, it uses it goes down the line. That if you give it a tuple, if you give it 2 elements, a and b, these are not defined yet here, it will look at a, and if it finds a tie, then it'll try to break that tie by going to b, etc. So let's go ahead and give it a value here of 1, and then a string, and I'll put in love here. Right? Let's put in another value over here, say 3, and another word and, right? And I don't want to type this all out, so let me go ahead and put the rest of this stuff in and ignore my semicolons here. Semicolons are okay in Python, they're just ignored, and it's not the Pythonic way of doing it, and I was screwing it up. So there we go. Love and structures, science, data, computer. Let's see what is in that heap, or what priority everything is in that heap. Right? And again, you'll note here that these are tuples. This is 3, that's the priority. And is the string, that's the thing that we're actually putting on the heap. You can imagine that as a symbol or a tree node or something else, right? Heap push, sorry. Heap push, heap push. Let's do that again. There. I love computer science and data structures. Right? Yes, I did preview that to make sure that it would actually work, right? So that's how you can use a heap in Python, Python 2 or Python 3. Now, how does a heap actually work? Again, you should be going back to Computer Science 2, checking out some of those 156 videos if you kind of lost it at the end of the semester, or if you took a Computer Science 2 course that didn't cover this kind of stuff. But just as a really quick review or reminder or preview, if you've not seen it ever before, let me go ahead and go back over here to the tablet and describe what a heap looks like. So what I'm going to do is let's take that array that we had before, but heapified. So 0, 1, 1, 3, 8, 5, 4. That was the array after it was heapified. The way that you visualize this is not as an array. You visualize it as a binary tree, a full binary tree. 0 is at the top, then 1, 1, then 3, 8, then 5, 4. And if I had, did I get everything? Yeah, that's everything. Right. I wish I hadn't repeated the ones, but let's suppose that there's something else over here. 5. We've already used 5. Let's go with 6. There we go. And you would imagine it like that. Now, the way that you should read this is 0, 1, 1, 3, 8, 5, 4, 6 is top to bottom, left to right. 0, 1, 1, 3, 8, 5, 4, 6. Right? Top, and then the next level, and then the next level, and the next level. Our observations here are that a heap is a full binary tree. It's not a binary search tree, if you're familiar with those. And consequently, it has a depth of order log n, where n is the number of elements in the tree. Okay? This is a consequence of it being a full tree. Another observation is that it has the heap property, the min heap property, that the child, or the key value in a node is less than or equal to both its children. Right? 0 is less than both 1 or 1. 1 is less than 3 and 8. That's why, yeah, 8 is out of order here. It doesn't matter. You can switch those around. The ordering here is not with respect to the entire list or the array. It's with respect to its parent. 1 is less than 5 and 4. 3 is less than 6. Right? Between the siblings, there is no relationship. Okay? But there is a transitive relationship that the grandparent of 6 is also going to be less than 6, right? Because of transitivity. This is less than its child is less than its child, and therefore the grandparent is less than its grandchild, right? Consequently, that gives us another observation. The min element is always the root. Right? And that's how we're getting these things to be efficient. I can always find the root in constant time because it's always at the top. It's always going to be the first element in the array representation. Its depth is logarithmic, and so the push and the pop operations, the insert and the retrieve, the get min, those operations are always going to be proportional to the depth. How? Right? How do we insert an element? So we say that we wanted to insert 7. I'm just going to demonstrate it here. If you want the full algorithms and the full details, again, you're going to have to go back to the videos. The way that we do this is, actually, no, I don't want to insert 7. I want to insert, say, 2. That'll be a good illustration. If I were to insert 7, you always insert it at the next available location. So level 1, level 2, and level 3, those are all full. Level 4, however, down here at the bottom, it has some room. It has a room for 7 other elements. We always insert at the last level and all the way to the left as an available spot, 2. Right? That maintains this fullness property, this full binary tree property. However, our heap property is now violated because 3 is not less than its child 2. No problem. We can go ahead and swap them. What was it? 2 and 3. And we've fixed the heap. If I were to insert -10, I would have to insert, insert it all the way at the bottom here at the next available spot. But I would have to fix the heap, and in this case, I would have to fix it all the way up. I would have to swap these two. I would have to swap these two. I would have to swap these two so that -10 can now become the new root node at the top. Right? That's fairly easy to do because all you have to do is traverse around this this array. And for those details, go to my other videos. You can, given an index I, you can find its left and right child really easy by going to 2i and 2i plus 1. Right? To illustrate what I mean there is, suppose that we are at the root. Where's its left child? If it's at index 1, then its right child is at index 2 times 1, 2. And its right child is at index 2 times 1 plus 1 over here. If I'm over at 8 here, it has an index of, note here that I'm using 1 indexing. You can burn the first one, or you can you're off by 1, you can subtract 1. So here, this is at index 5. How do I get to its left child? I have to go to index 10, which doesn't exist until after we insert 10, a negative 10 down here. And its right child is going to be at 5 times 2 plus 1 at index 11 over there. Okay? So that's fairly easy to do. And because you are always exchanging it up into the heap and then stopping at the root, that means that you're always going to be proportional to the depth. That means that you're always going to be order log n for all of your insert operations. What does remove? How does remove work? Right? Remember that you can't violate the heap property or the fullness property. So if I just eliminated 0 and saved it off so that I could return it, now I've got a gap in my tree. Right? I can't simply fill it in with one of its children. In this case, I probably could, but then that just shoves off the problem to lower in the tree. If I promoted this one up, then, or say I promoted this one up because it's a tie, then I would have to promote one of its children up, which would leave a gap somewhere in the tree. So the strategy for remove min is to replace the root with the last element and then fix the heap. All right, so we've already removed 0 from the equation here. What I do is, and let me back this up because that never got fixed. It looks like this now. What I do is I take the last element and promote it up here. After I've done that, the fullness property is now satisfied, but the heap property is not satisfied. So I simply do the same trick. I exchange it. I exchange it with its the minimum of its 2 children. Now in this case, the minimum is the same, so it doesn't matter if I go left or right. I'll simply exchange these two, and now I've got 1 and 3. The heap property is still not satisfied because 3 is not less than 2. So what I do is I can't promote 8 up here because then that would violate 8 is not less than 2. So again, I promote the minimum child. Right? 2 and 3 gets shoved down here. And then I still look at its child, and I see that its child is greater, and at that point the min heap property is now satisfied. That's how it works. So again, if you're confused about any of that, make sure that you're going back to Computer Science 2, and I've got some pre-prepared videos on it, or you can watch the videos from the actual offering from spring 2021. I don't see any other questions, so I'll go ahead and hold stop it there, and then we'll go ahead and pick it up there tomorrow.